Okay, so this is just a 15-minute presentation that is meant to give you a flavor for how to do resting state analysis in fMRI. As if task-based analysis wasn't complicated enough, there's also resting state connectivity analysis. So remember to do, so if we look through here, so this is your typical task space that we just went over in the last presentation that I did. And so you have some known time course of stimulation, and you measure some known, or you measure the fMRI time course response. And essentially what you're doing is you're correlating those two things together by creating regressors, in this case an odd and an even regressor. And this is the raw time course. And I'm going to solve this design matrix. I'm going to pull out hemodynamic response amplitudes for the odd blocks and the even blocks. And then I can do contrast and such. And then the contrast looks something like this, and you compute significance. You can see that you have activation in the occipital area and then the superior temporal gyrus area where primary auditory is. And so, that's basically the idea behind the task-based analysis. So with resting state, in 1995, it was noticed that if you just took a correlation between a single point in the brain and some other point in the brain, you could find these really, really high correlations. So in this waveform down here, actually, let me change this thing. In this waveform down here, you have the blue waveform, which comes from the isthmus cingulate, which is kind of in the back of the head. And you have this orange waveform, which comes from somewhere in the front of the head, in the frontal area. So these two points are, 10 centimeters apart, something like that. So they don't lie close to each other in the brain at all, and yet their correlation was really, really high, 0.46. And so the question came up as to whether these waveforms were being driven by endogenous neural activation. And so this has led to, as probably most of you know, this huge research effort to understand the connectivity. So the idea here is that these 2 points must be connected in some way. So the analysis for this is relatively straightforward. So here I have my orange voxel, my orange waveform from the frontal cortex. And instead of saying this equals to some weighted combination of task regressors, I have a regressor that I create from the isthmus cingulate. And so I say that that these two waveforms are the same by this weighting. And so this is just a general linear model. And so I just solve it the same way that I did, and I can compute the regression coefficients, which would be kind of like the hemodynamic response amplitude. In this case, it's more of a correlation between these waveforms. And I do that at every voxel, and I can compute contrast. And I can do everything now that I used to do with task-based data, I can do now with this seed-based resting state data. So part of what's interesting is being able to pick an interesting seed that you then correlate with the rest of the brain. So fortunately, FreeSurfer offers a huge number of seeds already when you run ReconAll. So so the basic idea is that you create the seed region by averaging all the waveforms inside of that particular region. So any ROI and FreeSurfer is fair game. You can also define your own in this conform space. So you basically just need to create a 1 millimeter 256 cubed volume that's in the same conform space, and set voxels to 1 and others to 0, and those ones will define a seed region. Typical for default mode is isthmus cingulate and precuneus. So here's an example of an analysis where I used the isthmus cingulate, which is right here, as the seed, and then correlated it with all of the rest of the left cortex here. And you can see this is a fairly classic default mode map. You're getting activation here in supramarginal gyrus, inferior parietal, and then up here in frontal areas, and you're getting this negative stuff in kind of places that you would expect. So inside of, for functional connectivity analysis, you just put the subject inside of the scanner. Subject just lies there, usually with eyes open, not doing anything in particular. Standard processing operations, motion correction, slice timing correction, smoothing. Usually the slice timing correction isn't as important because these endogenous fluctuations are generally pretty slow, somewhere around like 0.01 hertz to 0.05 hertz. So that's like one period every 100 seconds. So they're very slow. Nuisance regressor removal becomes much more important. Often what people do will be to compute the mean of the signal across the entire brain. This is called the global signal, and they will regress that out. This will make huge changes to your results. Oftentimes people will put in motion correction regressors as nuisance variables, sometimes with derivatives, sometimes with power. They will tend to filter out low frequency, like super low frequency fluctuations below this 0.01 hertz. And also people will often collect physiology, so they'll have a belt they put around their subjects where they can measure the inspiration and expiration. They might also have a finger cuff where they can measure the heart rate. And then they often will include regressors from white matter and CSF. So in this case, you would just average the time waveform, temporal waveform over all of the white matter voxels and put that in as a regressor, and then for all CSF voxels and put that in as a regressor. So in FSFast, you will configure the seed. So this is the same kind of model where you configure parameters, and that's done very quickly without any data, and then you do the analysis. So the configuration is called fcseed-config, and so here I tell it the seed region that I want is going to have a number of 1010. And 1010, if you look inside of this Freesurfer color table, is left isthmus cingulate. And then I give the configuration a name, and I tell it the functional subdirectory, which is bold. And I say that I want it to just compute the mean. There are other options as well. And then this is the name of the configuration file. So you can also, you can imagine easily how you would generalize this by simply changing this number to a different number. You would select a different seed region. And then you would run this fcseed -sesh. You give it the session ID, and you give it this configuration file, and it's going to go out and extract that seed from the isthmus cingulate. You can also do nuisance variables in a similar way. You would say fcc-config and say -wm. And so this is just a shorthand that says, give me all of the white matter regions of interest and create a nuisance regressor out of that. And there's also this VCSF file to extract out waveforms from CSF. If you want more information on this, you can go to this functional connectivity walkthrough on our wiki. And when you run FSFast, it's actually pretty similar in terms of how you run it. So you run this MK analysis -sesh, but there are a couple of things that are a little bit different. One, instead of giving it a paradigm file, you say you just give it a -no task. So at that point, it knows not to expect the stimulus timing because, of course, there isn't anything that's there. I say the task reg. So this is the seed that would have been created by fcseed-sesh, the previous command that we ran. Then you give it these nuisance variables, the CSF and the white matter. Here, I tell it to include motion correction regressors as nuisance variables. And then I set polyfit equal to 5 to make sure that it's filtering out very low frequencies. So after you configure the analysis, you don't need to run make contrast. One will be made for you. Then you just run SelectSAV3, ISXNCAT, MRIG, and LimFit, correct for multiple comparisons, do it for left hemisphere, right hemisphere, and subcortical. And then everything else is basically the same after that. Any questions? So the question is the thing that you're measuring when you do resting state the same hemodynamic response amplitude as you would measure during the task? And the answer is no. So when you do a task, you are correlating your task waveform against the bolt signal. And so that's going to give you the amplitude of the hemodynamic response in response to that particular task. So with this, you're actually taking two bold waveforms and you're correlating them together. So in principle, guess you could say that you could kind of interpret it as the hemodynamic response to, I mean it's not so easy to interpolate. Yeah, I mean you kind of interpret it the same way, that you have some neural signal at one point in the brain and it's causing some hemodynamic response in another part of the brain. But the problem is that you don't actually have a neural signal. You have a neural signal that's filtered by its own hemodynamic response. And you have a neural signal over here that's filtered by its own hemodynamic response. So when you correlate the two, you're not getting something out that's like an amplitude of a hemodynamic response out of it.